There has been an impact on the Big Bang theory. Our comprehension of the cosmos, laying down the groundwork for modern cosmology, is based on Einstein's theory and acknowledged as conventional cosmology. During the cosmic era following the Big Bang, everything begins with that explosive expansion, the origin of all matter, space, and energy. Approximately 13.8 billion years ago, this occurrence resulted in the vast cosmos we now observe. But recent advances in cosmology indicate that it is possible the Big Bang wasn't the absolute beginning. There may have existed something prior to it, which was equally crucial in the formation of the cosmos as we now understand it. This earlier phase is referred to as the cosmic inflation epoch, one of the most alluring aspects of modern cosmology. Prior to the Big Bang's hot, dense state, the universe experienced an exceptionally quick exponential expansion. During this period, the universe grew at a remarkable rate. To illustrate how extreme this growth was, if the cosmos had less mass than an atom at the beginning, it would have expanded significantly in size, more than the entire observable universe, within a tiny fraction of a second. This short span of rapid inflation was essential to the formation of the universe. When inflation stopped, the expansion's energy was transferred into space. This heated the universe, creating matter particles, everything we see now. For many, inflation is the predecessor to the present-day Big Bang. Though the inflation hypothesis is widely accepted, there are still many unanswered questions in cosmology. For example, what caused inflation? How long did it last? What made it stop? These unresolved issues are crucial for a more in-depth understanding of the cosmos's beginnings. Prior to inflation, the universe was an incredibly dense, tiny point of substance, often referred to as a singularity. The subsequent expansion led to the creation of atoms, stars, galaxies, and molecules. While the idea that everything started with a bang is attractive in modern cosmology, newer theories suggest a more complex picture. According to them, the universe experienced a period before inflation. Following the Big Bang, the universe grew exponentially, increasing in size at least 80 times. This rapid expansion was driven by an unknown energy source that filled the empty space. That energy, remaining after inflation ended, transformed into particles and heated the cosmos, leading to the hot, dense condition we call the Big Bang. Even though it began cold and empty, the inflationary phase laid the foundation for the development of everything we see. One of the most speculative modern concepts is the idea of eternal inflation, that inflation continued everywhere simultaneously, instead of stopping in all regions. This would result in several distinct bubbles, each potentially existing as a separate universe. Indeed, our cosmos could be just one patch among many. According to eternal inflation, there could be an infinite number of these worlds, each with its own set of physical laws and constants. This leads to the multiverse theory. Our world might be just one of a large, or possibly limitless, number of universes. If this hypothesis is accurate, it may help explain why life seems so perfectly suited to our cosmos. In a multiverse scenario, there might be a mix of physical laws. We just happen to live in a place where the conditions are ideal for stars, carbon, oxygen, and life to form. Despite speculative theories like the multiverse and eternal inflation, the inflation concept itself is supported by strong empirical evidence. The cosmic microwave background, CMB, provides this proof. The CMB is the oldest light in the universe, made available about 380,000 years after the Big Bang, when the cosmos had cooled enough for atoms to form. This made the universe transparent, allowing this light to travel through space ever since. Through research, cosmologists can essentially take a baby picture of the universe using this light, offering clues about the early universe. One of the most significant findings came from the European Planck spacecraft, which took high-resolution images of the CMB. These revealed tiny temperature fluctuations consistent with predictions made by inflationary theory, confirming that inflation is more than speculation. It's central to understanding how our universe began. To understand the Big Bang and what followed, we must merge two of Einstein's most important ideas in modern physics, the theory of general relativity and quantum theory. General relativity explains the universe on large scales, the behavior of stars, planets, and galaxies. Quantum theory describes the smallest scales, how subatomic particles behave. To answer questions like what space and time truly are, or how the cosmos started, scientists must create a theory that combines both. Such a theory might help us understand not just the Big Bang, but the conditions that caused it. One strange aspect of the universe is its enormous size. We can see approximately 47 billion light-years in every direction, making the observable universe about 94 billion light-years wide. This seems contradictory, given that the universe is only 13.8 billion years old. But the answer lies in the fact that space itself has been expanding, stretching the distances between objects over time. As a result, light from faraway galaxies has had to travel across a universe that's been expanding the entire time. Most experts believe the actual universe is much larger than the observable part, potentially infinite, with regions we may never observe because light from them hasn't reached us yet. Even though the universe may be endless, it doesn't necessarily mean there's something beyond it. Talking about outside the universe might be as meaningless as asking, what's north of the North Pole? Such questions stretch the boundaries of human understanding and drive new scientific breakthroughs. The development of theoretical physics has brought fresh ideas to explain these profound mysteries. One such framework is string theory, which proposes that the universe's fundamental building blocks are not particles, but tiny vibrating strings of energy. This theory also introduces extra dimensions beyond the familiar three of space, dimensions that may be curled up so tightly we can't detect them with today's technology. Loop quantum gravity is another approach gaining interest. It seeks to combine quantum mechanics and general relativity. According to this theory, space itself is quantized, made of discrete units, like pixels on a screen. This idea suggests the Big Bang might not have been a beginning, but a bounce from a previously collapsing universe. These alternative models challenge the traditional Big Bang story, offering new perspectives on how the cosmos began. While still speculative and incomplete, they are at the cutting edge of cosmology. Meanwhile, new observational tools are advancing. Telescopes like the James Webb Space Telescope, JWST, and future missions such as the Euclid Space Telescope aim to explore the early universe in unprecedented detail, capturing the light of the first stars and galaxies that formed just a few 100 million years after the Big Bang. Gravitational wave detectors like LIGO and Virgo are also opening new windows into the cosmos. They may eventually detect ripples in spacetime originating from the inflationary epoch itself, providing more direct evidence of inflation's impact. There was perhaps a chance that the cosmos would eventually collapse in a reverse Big Bang scenario, known as the Big Crunch, where gravitational forces would halt expansion and pull everything back into a dense point. However, the discovery of dark energy dramatically changed this outlook. Dark energy, a mysterious form of energy that permeates all of space, appears to be counteracting gravity. Instead of slowing down, the expansion of the universe is accelerating. This acceleration was first observed in the late 1990s through the study of distant supernovae. The implications were profound. Not only was the universe expanding, it was doing so at an ever-increasing rate. If dark energy continues to dominate the dynamics of the cosmos, several scenarios become possible. 1. The Big Freeze. This is currently the most widely accepted fate of the universe. As expansion accelerates, galaxies will drift farther apart, stars will burn out, and temperatures will drop close to absolute zero. In trillions of years, the universe may become cold, dark, and lifeless. 2. The Big Rip. If the force of dark energy increases over time, it could eventually tear galaxies, stars, planets, and even atomic particles apart. This catastrophic end would occur billions of years from now, as the repulsive power of dark energy overwhelms all other forces. 3. The Big Bounce. In more speculative models, especially those involving loop quantum gravity, the universe might not end in a freeze or rip but instead reverse into contraction and then bounce back into a new Big Bang-like expansion. This cyclic model suggests the universe may have had multiple births and deaths. While we still do not fully understand dark energy, its nature, origin, or exact properties, it currently accounts for approximately 68% of the total energy content of the cosmos. Combined with dark matter, 27%, and ordinary matter, 5%, our universe is mostly composed of things we can't directly see or touch. This realization has pushed scientists to redefine what it means to know the universe. At the cutting edge of this exploration lie quantum field theory, string theory, and quantum gravity models, each offering glimpses into how the fundamental forces and particles emerged. Many researchers hope that one day, a theory of everything will unify general relativity with quantum mechanics, explaining the universe's birth, structure, and fate. In essence, what began as a simple idea, that the universe started with a bang, has evolved into a grand, intricate mosaic involving inflation, dark energy, and the multiverse. From the first light of the cosmic microwave background to gravitational waves and deep field imagery from telescopes, we are continually assembling a more complete, though still mysterious, picture of our cosmos. And with every discovery, we come closer to answering the timeless questions. Why is there something rather than nothing? What lies beyond the visible horizon? And is our universe one of many? The universe could cease to grow and start crumbling under tremendous pressure, despite what it appears. There is an increase in dark energy and the distance between the universes is expanding fast. If this acceleration continues, the universe will continue to expand forever, ultimately arriving at a stage where the distance between galaxies is so great that they distance themselves from one another. In this scenario, the cosmos would cool off. Black would be destroyed by the stars, and everything would become empty. All matter and the universe would divvy up into fragments and, in the end, deteriorate, a result referred to as the universe freezing to death or heating to death. The story of the universe, as told from the start to the end, is one of the most deep and intricate scientific tales. While we have learned a lot about the history of the cosmos via the inflation theory and the investigation of the cosmic microwave background, there are still many unsolved concerns. What caused inflation? What prevented it? Why does something exist outside of the visible universe? How many alternative multiverses exist? As scientists, we keep exploring the cosmos using ideas and cutting-edge technologies that blend quantum mechanics with general relativity. We will surely learn more about these riddles by visiting them. The attempt to comprehend the universe is continuous, and every new finding brings us closer to answering the final inquiries about our existence. Examining the structure of the universe is not only a scientific undertaking but also poses philosophical questions about reality, existence, and our role in it. One of the main topics in cosmology is comprehending dark matter, which is believed to make up around 27% of the mass and energy content of the cosmos. Dark matter differs from ordinary matter. It neither produces, reflects, nor absorbs light, resulting in its undetectability and only being discernible by its gravitational effects on visible matter. Learning about dark matter is essential to understanding the formation and current dynamics of galaxies. Experiments and observations have provided further details on dark matter's characteristics. Despite this, its precise nature remains unknown. Several candidates have been suggested, including weakly interacting massive particles, WIMPs, and actions, but no concrete proof of dark matter particles has yet been found. However, the hunt is still ongoing. By combining astronomical observations and ground-based simulations, scientists are able to model the structures affected by dark matter. Dark energy also plays a significant role in this enigmatic field. It is the power speeding up the universe's expansion. Dark energy accounts for approximately 68% of the cosmos mass energy content. Its discovery was surprising and has given rise to multiple theories, including the cosmological constant and dynamic domains such as quintessence. Understanding dark energy is essential, as it will determine the universe's ultimate fate. Researchers are investigating how dark energy impacts celestial formations and whether it stays the same over time or changes. Along with dark matter, the study of dark energy and the development of cosmic structures offer insight into the universe's evolution. Measurements of the cosmic web, galaxy clusters and filaments, have demonstrated the clustering of matter under gravity, resulting in today's complex structures. Supercomputer simulations help scientists understand how these billions of structures have formed and continue to change. At the intersection of cosmology and astrobiology, scholars seek to understand the conditions that sustain life beyond Earth. The hunt for extraterrestrial life outside our solar system has intensified in recent years. Thousands of exoplanets orbiting stars have been discovered, and a few lie in habitable zones where liquid water might exist. By researching these distant places, scientists hope to discover more about the potential for life elsewhere in the universe and what that life might look like. Physics also plays a crucial role in cosmology. The pursuit of a unified theory that blends quantum mechanics and general relativity remains a challenge. Theories such as loop quantum gravity and string theory aim to unify these two frameworks and potentially explain phenomena like black holes and the origins of the universe. Technological advancements are enhancing our ability to observe and understand space. Telescopes like the James Webb Space Telescope are revolutionizing our understanding of the cosmos, offering unprecedented information about distant galaxies and cosmic events. As we continuously observe, we gradually piece together the puzzle of the universe, from its development to its destiny. In summary, the study of the cosmos encompasses numerous scientific disciplines and intellectual explorations. We investigate the fundamental forces that shape cosmic structures, search for alien life, and reflect humanity's deep curiosity about the universe. Each answer gained not only improves our understanding but deepens our appreciation for the universe's vastness and complexity. The link between observation and theory in cosmology is vital. New technologies, such as sophisticated detectors, machine learning, and advanced algorithms, are enhancing our capacity to analyze astronomical data. These tools help researchers sift through massive datasets, revealing patterns that could offer new insights into cosmic phenomena. One crucial field of study involves gravitational waves, ripples in spacetime caused by catastrophic events like black hole or neutron star collisions. Their discovery has opened a new window into the cosmos. Studying gravitational waves provides scientists with insights into extreme conditions and allows them to test theories of gravity in ways traditional methods cannot. In addition, the concept of cosmic time is fascinating. Unlike our everyday understanding of time as linear and uniform, cosmic time is influenced by the universe's expansion. This raises questions: is time absolute, or does it depend on the observer's motion and position? Such philosophical inquiries go hand in hand with scientific investigations, highlighting the complexity of the universe. The formation of the first galaxies and stars, what's known as cosmic dawn, is another focal point. Understanding this epic transformation helps clarify how the cosmos evolved from a hot, uniform state into the intricate systems we observe today. High redshift observations of galaxies provide essential clues about the processes at play during this crucial period, aiding scientists in constructing a timeline for the universe's evolution. As our understanding of the early universe deepens, we uncover more about the processes that govern the formation of stars, galaxies, and large-scale structures. Observations of the cosmic microwave background, radiation left over from the Big Bang, offer vital evidence of these early moments. Fluctuations in this ancient light reveal the seeds of all future structure, mapping the density variations that gravity would later amplify into galaxies and clusters. This insight has allowed cosmologists to refine the timeline of the universe's evolution, from the first moments of inflation to the gradual cooling and expansion we witness today. With each advancement in technology, we peer further back in time, capturing light that has traveled billions of years to reach us. Instruments such as the Atacama Large Millimeter Array, ALMA, and the European Extremely Large Telescope, ELT, are unlocking details of the earliest galaxies, how they merged, how stars formed within them, and how their radiation shaped the intergalactic medium. This deep exploration helps us understand not only how the cosmos formed, but why it looks the way it does now. Beyond galaxies and stars, black holes remain one of the most enigmatic and fascinating features of the universe. These regions of spacetime, where gravity is so strong that nothing, not even light, can escape, challenge our understanding of physics. Supermassive black holes, found at the centers of most galaxies, including our own Milky Way, influence the formation and evolution of their host galaxies through their immense gravitational pull and energetic jets. Recent discoveries, such as the imaging of a black hole's event horizon by the Event Horizon Telescope, provide direct visual confirmation of theoretical predictions made by general relativity over a century ago. These breakthroughs are not just scientific milestones, they symbolize humanity's ability to imagine, predict, and then witness the once invisible forces that shape the cosmos. In parallel, the concept of time travel, wormholes, and higher dimensions, once the domain of science fiction, is now explored in theoretical physics. Though still speculative, these ideas are rooted in the mathematics of general relativity and quantum theory. While we are far from creating a real-time machine or traveling through a wormhole, the pursuit of these theories opens doors to reimagining our place within the fabric of reality. Cosmology, therefore, is not just about cold equations and distant galaxies. It is about understanding the ultimate questions: where did we come from? Why is there something rather than nothing? Is the universe finite or infinite? Are we alone, or one of many forms of life scattered across the stars? Every observation, from the redshift of a distant galaxy to the faint signal of a dying star, carries a piece of the universe's autobiography. With every launch, every equation solved, and every theory refined, we write another chapter in the story of existence. And the story is far from over.